What if the very first complex molecules in our universe, those tiny sparks of chemistry that set the stage for life itself, weren't just random accidents, but clues to a grand cosmic puzzle? Picture this, drifting through the cold, empty vastness of space over 13 billion years ago. Invisible fragments began to dance, collide, and bond in ways we're only now beginning to understand. These weren't just simple compounds, they were the universe's first experiments in complexity, the silent architects of everything that followed. And here's the staggering part. We've uncovered not one, not two, but 30 breathtaking theories about how these molecular pioneers came to be. Some are elegant, some are wildly unexpected, and a few might just rewrite everything we thought we knew about the origins of life. Think about that for a moment. The molecules that eventually led to stars, planets, and even you didn't just appear out of nowhere. They emerged from chaos, shaped by forces so immense and conditions so extreme, it's a miracle they existed at all. Was it the searing heat of newborn stars that forged them? The crushing pressures inside ancient clouds of gas? Or could there have been something even stranger at work, cosmic lightning, interstellar dust, or perhaps processes we haven't even imagined yet? The answers aren't just buried in textbooks, they're hidden in the very fabric of the universe, waiting for us to piece them together. That's exactly what we're about to do. Over the next minutes, we're going to unravel these 30 theories one by one, each one a thread in the tapestry of our cosmic origins. You'll hear ideas that sound like science fiction, like molecules assembling on the surface of asteroids, or complex chemistry sparking in the hearts of dying stars. You'll discover how scientists are recreating the dawn of time in labs, simulating the conditions that might have birthed these first molecules. And by the end, you won't just know the theories, you'll feel the weight of that incredible moment when the universe took its first step toward creating everything we see today. So settle in, because we're about to journey back to the very beginning, to a time when the building blocks of life were nothing more than whispers in the dark. The story starts now. Let's start with one of the most famous theories, the Primordial Soup Hypothesis. Imagine Earth 4 billion years ago, a planet still cooling from its violent birth, with oceans simmering under an atmosphere thick with volcanic gases. In this hostile world, something extraordinary happened. The simple chemicals dissolved in those ancient waters, ammonia, methane, hydrogen, began to react, driven by the relentless energy of lightning strikes and the unfiltered fury of ultraviolet radiation from the young sun. This chaotic mix, this so-called primordial soup, might have been where the very first complex molecules took shape. The idea gained legendary status in the 1950s when scientists Stanley Miller and Miller-Urey decided to test it in their lab. They recreated Earth's early conditions in a glass apparatus, boiling water for the ocean, a mix of gases for the atmosphere, and electrodes to simulate lightning. Within days, the experiment produced something astonishing: amino acids, the building blocks of proteins, swirling in their miniature primordial ocean. It was a revelation, proof that life's ingredients could emerge from simple chemistry. But here's where things get interesting. While the Miller-Urey experiment became a cornerstone of origins research, later discoveries raised new questions. We now know Earth's early atmosphere might not have been exactly like their lab setup. Some scientists argue volcanic gases or even extraterrestrial delivery via comets played a bigger role. Others point out that amino acids alone don't spontaneously assemble into life. They need a way to link up to form chains, and that requires something more. Yet the primordial soup hypothesis endures, not because it's perfect, but because it captures something fundamental. Whether in Earth's oceans or the icy geysers of Saturn's moon Enceladus, the idea that energy acting on simple chemicals can spark complexity remains a powerful lens for understanding how molecules might have taken their first steps toward life. It's a reminder that sometimes the most revolutionary ideas start with a simple question: what if? Now let's plunge into the depths of the ocean where crushing pressures and scalding temperatures might have cooked up the universe's first complex molecules. Far from the sunlit surface, hydrothermal vents spew superheated water packed with minerals, creating otherworldly chimneys on the seafloor. These aren't just geological curiosities, they could be the very laboratories where life's ingredients first assembled. Picture a vent system like the Lost City, a sprawling network of white towers near the mid-Atlantic ridge. Here, water seeping through Earth's crust reacts with mantle minerals, then erupts at over 300 degrees Fahrenheit. But instead of a toxic wasteland, these conditions may have been perfect for chemistry. The vents provide a steady flow of energy, not from sunlight but from chemical gradients. Hydrogen sulfide mingles with iron and nickel, while porous rock formations act like microscopic reaction chambers, concentrating molecules and giving them time to link up. And the evidence: scientists have found amino acids clustering near modern vents, suggesting these environments don't just destroy organic compounds, they actively create them. Even more compelling, the mineral structures in vents resemble the scaffolding of cell membranes, hinting at how early molecules might have organized into larger systems. Astrobiologists love this theory because it doesn't rely on luck. It's a repeatable process, one that could be happening right now on ocean worlds like Europa or Enceladus. But the vent hypothesis isn't without its challenges. Critics point out that while vents excel at producing simple molecules, bridging the gap to true complexity remains murky. Could delicate chains of RNA or proteins survive the violent temperature shifts and acidic waters? Some researchers think the answer lies in cooler, alkaline vents, where gentler conditions might have allowed molecules to stabilize and interact. What makes this theory so captivating is its universality. Vents aren't unique to Earth. Any watery world with geological activity could host them. So if we're searching for life's origins, the answer might not be in the skies or the soil, but in the eternal darkness of the deep. What if the building blocks of life didn't even originate on Earth? That's the radical proposition at the heart of Panspermia. The idea that complex molecules, or even the precursors to life itself, could have been delivered to our planet by celestial hitchhikers like comets and meteorites. Imagine this: drifting through the void for eons, a rugged space rock carrying microscopic cargo finally plunges through Earth's early atmosphere, splashing into a shallow sea. In that moment, the chemistry of our world changes forever. This isn't just science fiction. In 1969, the Murchison meteorite crashed into Australia, and when scientists analyzed its fragments, they found over 90 different amino acids, many of which are identical to those used by life on Earth. Even more astonishing, some of these molecules displayed a slight preference for one molecular orientation over its mirror image, a trait called chirality that's fundamental to biological systems. It was as if the universe had already been tinkering with life's ingredients long before Earth existed. But here's where the debate ignites. Critics argue that while meteorites like Murchison prove space is littered with organic material, that doesn't necessarily mean these molecules seeded life. After all, amino acids can also form naturally on Earth, and contamination after landing is always a concern. Some researchers point out that the intense heat of atmospheric entry would destroy delicate compounds, though others counter that the interiors of larger asteroids could remain cool enough to protect their precious cargo. The implications are staggering. If Panspermia is even partially correct, life's origins aren't tied to any single planet. They're woven into the fabric of the cosmos itself. Recent missions like Japan's Hayabusa 2 have only deepened the mystery, retrieving samples from the asteroid Ryugu that contain uracil, a key component of RNA. Meanwhile, observations of comets like 67P reveal they're rich in organic molecules, supporting the idea that these icy wanderers could have been molecular delivery trucks for young planets. Yet the biggest question remains unanswered. Did these cosmic travelers merely supply raw materials, or could they have carried something even more complex? A fringe but fascinating twist on panspermia suggests that entire microbial life might survive interstellar journeys shielded deep within rocks. While evidence for this remains elusive, it forces us to rethink the boundaries of life's potential. Whether as simple chemical kits or as dormant biological cargo, the idea that we might owe our existence to the stars challenges everything we assume about our place in the universe. Now let's step outside our solar system entirely and venture into the vast, frozen nurseries of interstellar space. Floating between the stars, colossal molecular clouds, some stretching light years across hold temperatures just a few degrees above absolute zero. These aren't empty voids, they're bustling chemical factories where the raw ingredients of the universe quietly assemble into something far more complex. And within their icy depths, astronomers have spotted something extraordinary: the faint fingerprints of molecules like glycine, the simplest amino acid, hinting that life's building blocks might have been forged in the coldest corners of the cosmos. How is this even possible? At first glance, these clouds seem utterly hostile to chemistry. The near-perfect vacuum means atoms rarely collide, and the bitter cold should freeze any reaction in its tracks. But here's the twist: that extreme environment might actually enable certain reactions. Dust grains coated in ice act as tiny laboratories, trapping atoms long enough for them to bond. Ultraviolet light from nearby stars, though faint, can kickstart processes by breaking apart simple molecules like water or carbon monoxide, releasing reactive fragments that glom onto each other. And over millions of years, these slow, steady interactions could build up surprising complexity. The evidence is mounting. Radio telescopes like ALMA have detected organic molecules in these clouds, from methanol to formaldehyde compounds that serve as stepping stones to amino acids. In 2020, researchers even found phosphine, a molecule linked to life on Earth, in the distant cloud known as W51. These discoveries suggest chemistry in space isn't just possible, it's prolific. Yet puzzles remain. While we've spotted precursors to glycine, confirming its actual presence in these clouds is tricky. The reactions are achingly slow, and competing processes might destroy fragile molecules faster than they form. Some scientists argue that while space clouds could contribute to life's ingredients, they might not be the primary source. Others counter that the sheer scale of these regions, with trillions of tons of organic material, means even rare reactions could produce vast quantities over cosmic time. What makes this theory so compelling is its scope. If molecular clouds are indeed cosmic kitchens, then the story of life doesn't begin on planets at all. It begins in the darkness between stars, where chemistry quietly lays the groundwork for everything to come. Next time you look up at the night sky, remember, those patches of blackness aren't empty, they're simmering with possibility. But what if the key to life's origins wasn't just about energy or chemistry, but about place? Picture this: a primordial shoreline where the tides ebb and flow, but instead of ordinary sand, the beach glitters with radioactive minerals like uranium and thorium. This isn't the setting for a post-apocalyptic novel, it's the radioactive beach hypothesis, a daring idea that suggests these seemingly hostile environments might have been the perfect incubators for the first complex molecules. Here's how it could have worked. As waves washed over these mineral-rich sands, they'd create shallow, temporary pools where organic compounds could concentrate. The radioactivity, rather than destroying everything, would provide a steady trickle of energy, like a slow-burning fuse, enough to drive chemical reactions without obliterating fragile molecules. Uranium's decay, for instance, releases alpha particles that can break apart water molecules, generating reactive hydrogen and oxygen fragments eager to bond with nearby carbon and nitrogen. Meanwhile, the tidal cycle itself acts as a natural laboratory, wetting and drying the compounds over and over, a process scientists know can help simple molecules link into long chains. And the evidence: researchers have recreated these conditions in labs, exposing amino acids to low-level radiation in the presence of radioactive minerals. The results are striking. Not only do the molecules survive, they thrive, forming more complex structures than in controlled, non-radioactive environments. Even more compelling, ancient rock formations like the Oklo natural nuclear reactors in Gabon, Africa, show that uranium-rich zones can sustain delicate chemical processes for millennia. Critics, of course, raise valid concerns. Wouldn't prolonged radiation damage delicate organic molecules? Proponents counter that the dose matters. Low to moderate levels might act like a catalyst, while extreme exposure would be destructive. Another puzzle is whether these beaches were common enough to make a difference, but supporters argue that radioactive minerals weren't rare in Earth's youth. In fact, they might have been more abundant before erosion and plate tectonics scattered them. What makes this theory so captivating is its sheer unexpectedness. We often think of radiation as a force of destruction, yet here, it might have been a silent architect shaping the very foundations of life in the unlikeliest of places. It's a reminder that in the search for origins, sometimes the answers lie not in the obvious, but in the places we'd least think to look. Now imagine a world where the first complex molecules didn't just form randomly, they had help from an unlikely architect, mud. That's the essence of the clay template theory, which suggests that the delicate layers of certain minerals might have acted as nature's first blueprints, guiding simple chemicals into precise arrangements that could eventually lead to life. Picture a shallow pool on early Earth, its edges lined with slick, layered clay like montmorillonite or kaolinite. To the naked eye, it's just dirt, but under the right conditions, these unassuming sheets could have been the universe's first molecular assembly lines. The magic lies in clay's structure. These minerals form stacks of ultra-thin layers, each one riddled with tiny pores and charged surfaces that attract and hold organic molecules like a magnet. Amino acids or nucleotides drifting into these gaps would find themselves neatly aligned, almost as if the clay were nudging them into position. And here's where it gets remarkable. Experiments show that clay doesn't just organize molecules, it speeds up their reactions. In lab simulations, clays have been found to catalyze the formation of RNA-like chains hundreds of times faster than in free solution. It's as if the mineral's surface acts like a microscopic workbench, holding components steady while they snap together. One of the most compelling pieces of evidence comes from the work of chemist James Ferris, who demonstrated that clay minerals could stitch together nucleotides, the building blocks of RNA, into strands up to 50 units long. That's not just a random soup of chemicals, it's a rudimentary system capable of storing information, a critical step toward life. Even more intriguing, clays selectively bind certain molecules over others, potentially explaining why life favors specific amino acids or sugar configurations. But like all theories, this one has its skeptics. Some argue that while clays excel at organizing small molecules, bridging the gap to true biological complexity requires more than just scaffolding. Others point out that not all clay-rich environments are equally conducive. pH, water flow, and mineral composition all play crucial roles. Yet even critics admit the theory's elegance. It doesn't rely on rare events or extreme conditions. Clay is abundant, durable, and its catalytic properties are reproducible under plausible early Earth scenarios. What makes this idea so fascinating is its simplicity. In a universe where we often look to the stars for answers, the key to life's origins might have been beneath our feet all along, hidden in the quiet, patient chemistry of earth and water. It's a humbling reminder that sometimes the most profound revolutions begin with the most ordinary tools. The searing heat of a volcanic eruption isn't just destruction. It could be the crucible where the universe's first complex molecules forged their existence. Picture Earth's early atmosphere, thick with plumes of carbon dioxide and nitrogen belching from countless volcanoes. A toxic mix to us, but a playground of potential for chemistry. In these superheated jets, gases that would normally ignore each other are forced together under extreme pressure, sparking reactions that might have birthed the precursors to life itself. Modern volcanoes offer tantalizing clues. Take Kilauea in Hawaii, where scientists have detected traces of formaldehyde and hydrogen, cyanide, two molecules notorious for their role in prebiotic chemistry lurking in its emissions. These aren't just random byproducts, they're the exact kind of intermediates that could link simple gases to more sophisticated organic compounds. Laboratory experiments back this up. When researchers simulate volcanic conditions by heating carbon dioxide and nitrogen to thousands of degrees, then rapidly cooling the mix, they observe the spontaneous formation of amino acids like glycine. It's as if the violent dance of eruption and quenching creates a perfect storm for molecule building. But what makes this theory stand out is the sheer scale of the process. Unlike delicate reactions in tidal pools or icy space clouds, volcanic synthesis is brute force chemistry, powered by the planet's own geothermal fury. A single eruption could pump tons of reactive gases into the atmosphere, where lightning or ultraviolet light might further sculpt them into complexity. Some researchers even speculate that volcanic aerosols, tiny particles suspended in the air, could have acted as floating reaction chambers, concentrating chemicals and shielding them from destructive radiation. Critics, however, highlight a paradox. While volcanoes excel at creating small organic molecules, their environments are notoriously harsh. Wouldn't the same heat and acidity that forge these compounds also rip them apart? Proponents counter that not all volcanic zones are equally extreme. Subsurface hydrothermal systems, where hot gases percolate through porous rock, might offer a Goldilocks zone, enough energy to drive reactions but enough stability to preserve the results. Recent studies of Iceland's volcanic fields reveal pockets where temperatures and pH levels align precisely with those needed to stabilize amino acids. The implications stretch beyond Earth. If volcanic chemistry can seed organic molecules here, why not on Mars, where ancient lava flows once raged, or Venus, whose hellish atmosphere might hide similar processes in its sulfuric clouds? This theory forces us to reconsider volcanoes not as mere geologic features, but as potential cosmic engines of creation, turning barren landscapes into cradles for complexity. It's a reminder that sometimes the most violent forces in nature might also be the most generative. Lightning doesn't just split the sky, it might have split the path to life itself. Imagine Earth's early atmosphere crackling with constant electrical storms, each bolt unleashing energies dwarfing anything we see today. These weren't just flashes of light. They were cosmic chemistry sets, ripping apart simple gases and welding them back together into the universe's first complex molecules. This is the electric spark polymerization theory, where raw atmospheric ingredients like methane, ammonia, and water vapor could have been transformed into sugars, amino acids, and even nucleotides, the very letters of life's genetic code, all in the white-hot instant of a lightning strike. The concept gained fame with the Miller-Urey experiment, but recent research has taken it further. Modern labs now simulate these primordial lightning strikes with precision, zapping gas mixtures not just with sparks, but with plasma jets mimicking volcanic discharges or asteroid impacts. The results are staggering. Within minutes, these energetic bursts generate ribose, a sugar critical for RNA, nucleobases like adenine, and even short chains of amino acids. It's as if the violence of the spark forces molecules into configurations they'd never achieve through gentle chemistry alone. One breakthrough came in 2018, when chemists at the Czech Academy of Sciences demonstrated that electric discharges could create all 4 RNA nucleobases simultaneously, something previously thought impossible outside living cells. Even more compelling, the reactions showed selectivity, favoring biologically relevant molecules over random variants. This hints that lightning might not just create organic soup, but curate it, nudging chemistry toward the specific compounds life would later adopt. Yet mysteries linger. Critics point out that while sparks excel at making small molecules, assembling them into long, stable polymers like RNA strands requires more than momentary energy. Some propose that tidal pools or hydrothermal vents could have provided the next step, concentrating these spark-borne compounds for further assembly. Others argue that repeated zapping, like a drumbeat of lightning across millennia, might have built complexity over time. What makes this theory electrifying literally is its raw universality. Lightning isn't unique to Earth. Venus crackles with it, Jupiter's storms dwarf ours. Even distant exoplanets with turbulent atmospheres could be hosting similar molecular alchemy right now. So when you see lightning today, you might be witnessing an echo of the process that set the stage for life's grand opening act. Sunlight isn't just warmth and energy, it could have been the universe's first chemist. Imagine a barren, waterless landscape under relentless ultraviolet glare, where rocks like titanium dioxide hum with activity under the harsh rays. This isn't a post-apocalyptic wasteland. It's a laboratory where UV light and mineral surfaces conspire to forge complex molecules without a single drop of liquid. And the most mind-bending part, we've seen it happening not just in labs, but on places like Mars, where the same brutal conditions might have once sparked cosmic-scale chemistry. The process is deceptively simple. When UV photons slam into certain minerals, they knock electrons loose, creating reactive hotspots on the surface. These charged patches become tiny docks where carbon monoxide, nitrogen, and other simple gases can anchor and rearrange into surprising complexity. Titanium dioxide, a common mineral found in everything from sunscreen to Mars' rusty soil, is a superstar here. Experiments show it can catalyze the formation of formaldehyde, methanol, and even glycine, all under bone-dry conditions that would normally stifle chemistry. Mars offers an eerie test case. The planet's surface is bathed in unfiltered UV radiation, its thin atmosphere doing little to soften the blow. Yet recent missions have detected organic molecules clinging to Martian soil, precisely where minerals like titanium dioxide are abundant. Scientists simulating these conditions in Mars-like chambers watched as UV light transformed simple carbon compounds into more elaborate structures, no water required. It's as if the very hostility of the environment, the dryness, the radiation becomes the engine for creation. But could this really rival Earth's water-based chemistry? Critics argue that while surface reactions produce intriguing molecules, they lack the solvent magic of liquid water, which helps molecules move, collide, and evolve. Yet proponents counter with an ingenious twist. What if these dry-formed compounds later washed into temporary pools during rare wet periods? The minerals might act as a slow cooker, stockpiling organic material over eons until water briefly mobilizes them for the next step. The implications ripple outward. If UV-driven chemistry works on Mars, why not Titan's dunes or the scorching plains of Venus? Even exoplanets orbiting violent young stars bombarded by ultraviolet flares might host this stealthy molecular factory. It's a humbling thought. The same light that burns skin and fades paint could have been the silent midwife to life's first whispers. Deep in the perpetual shadows of ancient craters or beneath the frozen crusts of polar wastelands, the universe may have been quietly stockpiling its most precious molecular ingredients. These aren't just barren wastelands, they're cosmic deep freezers, where temperatures plunge hundreds of degrees below zero, creating natural traps for wandering molecules. Picture a comet or asteroid with permanently shadowed regions, so cold that any volatile compound drifting in water, ammonia, even complex organics, instantly freezes in place, accumulating layer upon layer over millions of years. No scorching sunlight to break them apart, no radiation to shred their delicate structures. just perfect preservation, like a celestial pantry slowly filling with the raw materials of life. This phenomenon isn't hypothetical. We've seen it firsthand on Mercury, where NASA messenger probe discovered vast glaciers of water ice lurking in polar craters, places sunlight hasn't touched for billions of years. Even more telling, the Moon's Shackleton crater harbors frozen reservoirs containing methane, carbon dioxide, and traces of organic molecules. If these survival bunkers exist today, imagine how much more potent they'd have been 4 billion years ago, during the late heavy bombardment, when comets and asteroids rained down constantly, each one potentially seeding these cold traps with fresh organic cargo. Laboratory experiments reveal something remarkable about these frozen archives. When scientists simulate space conditions by chilling mixtures of water, methanol, and ammonia to near absolute zero, then zap them with radiation mimicking cosmic rays, something extraordinary happens. Instead of destroying the molecules, the energy actually helps them reorganize into more complex structures like cyanides and even amino acids. The ice acts as both a shield and a reactor, absorbing harmful radiation's energy while giving molecules time to rearrange. It's a paradox. The same cold that preserves also catalyzes, creating a slow-motion chemistry lab where complexity builds over eons, yet challenges remain. While cold traps excel at accumulation, could they also facilitate the next critical step, bringing these molecules together in ways that spark life? Some researchers propose that occasional asteroid impacts might provide the answer. A well-placed strike could melt portions of these icy deposits, creating temporary pools where concentrated organics could interact. Others suggest volcanic heat might seep through cracks, creating localized warm zones amid the frozen wastes. The beauty of this theory lies in its versatility. These traps aren't confined to planets. They could exist on dwarf planets like Pluto, moons like Europa, or even rogue interstellar objects drifting between stars. What makes cold trap accumulation so compelling is its inevitability. In a chaotic young solar system where destruction was the norm, these shadowed sanctuaries offered molecules something rare: time. Time to accumulate, time to react, and perhaps, given enough millennia, time to take that first tentative step towards something greater. The universe didn't need a miracle, just a dark, quiet corner where chemistry could work undisturbed. Asteroid impacts aren't just destructive. They might be the explosive forges where the universe's first complex molecules were hammered into existence. Picture a typical day on early Earth 4 billion years ago. The sky darkens as a mountain-sized space rock screams through the atmosphere at 50,000 miles per hour, slamming into the surface with the energy of 1,000,000 nuclear bombs. The blast vaporizes rock, melts continents, and sends tsunamis racing across the globe. But amid this apocalypse, something extraordinary happens. The unimaginable heat and pressure of the collision transforms simple gases like carbon dioxide and nitrogen into amino acids, sugars, and even nucleobases, the very ingredients of life born from chaos. This isn't speculation. Scientists have recreated these cataclysmic conditions in labs using high-powered guns and laser blasts to simulate asteroid strikes. In one groundbreaking experiment, researchers filled a steel capsule with water, ammonia, and methanol, simple compounds abundant on young Earth, then subjected it to a shockwave with pressures exceeding 600,000 times Earth's atmosphere. The result, glycine and alanine, two of life's essential amino acids, formed in milliseconds. It turns out the shockwaves from impacts don't just obliterate, they rearrange, forcing molecules into configurations they'd never achieve under normal conditions. The real-world evidence is even more compelling. Take the Sudbury Basin in Canada, a 250-kilometer wide scar from an ancient impact. Analysis of its rocks reveals not just metals and melted stone, but traces of complex carbon compounds. Similarly, the Murchison meteorite, which itself survived a violent cosmic journey, carries over 90 amino acids. Together, these clues paint a picture. impacts might act as both destroyers and creators, their fury forging molecular complexity in the very instant they seem to erase it. Critics, however, raise a valid point. Could delicate organic molecules survive the aftermath of such violence? The answer might lie in the Goldilocks zones of impacts, regions where temperatures and pressures were extreme enough to drive reactions, but not so severe as to incinerate everything. Smaller impacts or the fringes of larger ones could have provided these pockets of productive chaos. Some researchers even propose that the steam-rich plumes ejected by strikes created temporary chemical reactors in the atmosphere where molecules could cool and combine before raining back down. What makes this theory so gripping is its scale. Earth wasn't just bombarded occasionally, it endured a relentless pummeling during the late heavy bombardment, with thousands of city-sized asteroids striking over a few 100 million years. Each impact was a potential chemistry set, a fleeting chance for molecules to leap forward in complexity. And if it happened here, why not on Mars, where ancient impacts left their own organic signatures, or Europa, where icy crusts might have shielded impact-borne compounds? The universe, it seems, doesn't need gentle labs to craft life's building blocks sometimes. All it takes is a well-placed cosmic hammer. Beneath the bubbling surface of ancient hot springs lies a hidden world of microscopic tunnels, labyrinths so tiny they're invisible to the naked eye, yet vast enough to have potentially cradled the universe's first complex molecules. These are geothermal pore networks, nature's nanoscale laboratories where heat, water, and rock conspire to create something extraordinary. Picture a sponge made of volcanic stone, its countless pores each no wider than a human hair, submerged in mineral-rich waters heated by Earth's molten core. Within these cramped chambers, molecules weren't just randomly colliding, they were being sheltered, concentrated, and methodically rearranged by forces we're only beginning to understand. What makes these pores so special? Three things: confinement, catalysis, and protection. First, the narrow walls force molecules into close quarters, dramatically increasing the odds they'll interact. Experiments show that reactions in confined spaces can accelerate by orders of magnitude compared to open water. Second, the mineral surfaces, often iron or nickel-bearing clays, act like chemical matchmakers, lowering the energy needed for bonds to form. And third, the pores shield fragile compounds from destructive ultraviolet radiation or sudden temperature swings that would rip them apart elsewhere. It's as if early Earth built billions of microscopic test tubes, each one a perfectly tuned reactor for molecular innovation. The smoking gun comes from modern analogs like Yellowstone's thermal pools. Scientists sampling these waters have discovered something astonishing. The highest concentrations of organic molecules aren't in the open pools, but trapped inside the porous rock itself. Even more compelling, lab simulations using artificial silica pores have produced peptide chains, short strings of amino acids, under conditions mimicking geothermal vents. The pores don't just host reactions, they select for complexity, favoring molecules that can withstand the environment's ebb and flow. But here's where the theory gets truly elegant. These networks aren't static. As hot water percolates through the rock, it creates dynamic gradients, zones of differing temperature, pH, and chemical composition just millimeters apart. A molecule might form in a scorching pore, then get flushed into a cooler one where it stabilizes, then drift into another where it links with neighbors. This natural conveyor belt could have allowed step-by-step assembly of increasingly sophisticated structures, all without any external guidance. Critics argue that while pores excel at small-scale chemistry, bridging the gap to true biological systems remains a hurdle. Yet recent studies on iron sulfide pores suggest some might have even mimicked cell-like compartments, trapping molecules inside semi-permeable barriers. Whether as stepping stones or final workshops, these hidden labyrinths remind us that sometimes the universe's grandest experiments happen in the smallest of spaces. Deep beneath the ocean's surface, where scorching vents meet frigid seawater, a tiny metallic structure could hold the secret to life's earliest chemical tricks. This is the iron-sulfur world hypothesis, and it suggests that clusters of iron and sulfur atoms simple enough to form spontaneously in nature might have served as the universe's first molecular machines, kicking off reactions that would eventually lead to life. Picture a hydrothermal vent's rocky face studded with microscopic nodules of pyrite, also known as fool's gold. To the untrained eye, they're just mineral curiosities. But zoom in closer and you'll find something astonishing. These tiny metallic flecks bear an uncanny resemblance to the active sites of modern enzymes, the very proteins that power every cell in your body today. The connection isn't superficial. Take nitrogenase, an enzyme crucial for life's nitrogen cycle. At its heart lies an iron-sulfur cluster almost identical to those found near vents. Or consider hydrogenase, which helps organisms harness hydrogen gas. It too relies on iron-sulfur chemistry. These aren't coincidences, they're molecular fossils, hints that life might have co-opted pre-existing mineral catalysts rather than inventing them from scratch. Laboratory experiments back this up. When scientists simulate vent conditions by mixing iron, sulfur, and simple gases like carbon monoxide, the resulting clusters can catalyze reactions strikingly similar to biological processes, from carbon fixation to electron transfers. But how could random mineral patches evolve into sophisticated catalysts? The answer lies in their environment. Hydrothermal vents aren't static, they're dynamic, with temperature gradients and shifting chemical concentrations creating endless combinatorial possibilities. An iron-sulfur cluster formed in one zone might get swept into another where it encounters new molecules, subtly altering its structure. Over millennia, this natural selection of minerals could have honed increasingly efficient catalysts, bridging the gap between geology and biology. Critics point out that while iron-sulfur clusters excel at simple reactions, they lack the precision of true enzymes, yet recent discoveries keep blurring that line. In 2022, researchers at University College London created synthetic iron-sulfur peptides that not only catalyzed reactions but showed rudimentary self-replication, a ghost of how inorganic chemistry might have crossed into the organic realm. What makes this theory so compelling is its simplicity. The universe didn't need a miracle to jumpstart life's chemistry, just iron, sulfur, and the patient churn of Earth's primordial waters. Next time you see a rusty nail or a chunk of pyrite, remember, these humble materials might have been the scaffolding for existence itself. High above the surface of a young Earth, where the air was thick with methane and nitrogen, an invisible shield of tiny particles might have been quietly rewriting the rules of chemistry. These weren't just specks of dust, they were photochemical aerosols, microscopic lenses floating in the atmosphere, each one a self-contained laboratory where sunlight could work its magic. Picture Titan's hazy orange skies today, where complex organic molecules rain down despite surface temperatures of -200 degrees Fahrenheit. That same process could have unfolded here billions of years ago, with atmospheric hazes acting as both umbrella and alchemist, protecting delicate molecules below while forging new ones above. The secret lies in the aerosol's dual nature. On one hand, their opaqueness scatters ultraviolet radiation that would otherwise sterilize the surface, a natural sunscreen for emerging chemistry. But within the particles themselves, that same light becomes a tool. Laboratory simulations using reaction chambers filled with methane and nitrogen gas show that when you irradiate these mixtures to mimic early sunlight, the resulting aerosols become factories for startling complexity. Scientists at NASA, a Goddard Space Flight Center, recreated Titan-like conditions and watched as simple gases transformed into tholins, organic goo containing amino acids, nucleotide bases, and even the precursors to pigments found in living cells. What makes these atmospheric reactions so ingenious is their scalability. Unlike localized vents or beaches, aerosols would have blanketed the entire planet, creating a global network of chemical reactors. Some models suggest Earth's prebiotic haze might have been 10 times thicker than today's pollution, meaning trillions of particles were simultaneously churning out organic material. And because aerosols have layered structures like microscopic onions, they can host different reactions in their cores versus their shells. A molecule formed in one zone could migrate outward, encountering new reactants as it goes. Modern experiments reveal even more tantalizing details. When researchers at the University of Hawaii added trace metals like iron to their aerosol simulations, the yield of biologically relevant compounds skyrocketed. It turns out these metals act like molecular shepherds, guiding reactions toward useful configurations. Even more remarkably, some aerosols spontaneously develop electrical charges, potentially allowing them to selectively attract certain molecules, a rudimentary form of chemical selection. Yet puzzles remain. Would these sky-borne molecules have efficiently reached the surface or gotten trapped in atmospheric cycles? Studies of modern volcanic plumes suggest an answer. When aerosols grow large enough, they act like parachutes, gently ferrying their cargo downward. And once there, they might have encountered something extraordinary, a surface already primed with ponds or tidal zones, ready to receive this atmospheric gift. The implications stretch beyond Earth. If hazes can spawn such richness on worlds as hostile as Titan, then exoplanets with similar atmospheres might be hidden cradles of chemistry we've barely begun to imagine. It's a humbling thought. The same photochemical processes that color alien skies could be universal architects, painting the first strokes of complexity across countless worlds. Cosmic rays, those invisible bullets of energy screaming through space at nearly light speed, might have been the universe's original molecular sculptors. Far from random destruction, these high-energy particles could have acted like cosmic chisels, carving simple chemicals into the first complex structures capable of kickstarting life. Picture a frigid dust grain drifting in deep space, its surface coated with a thin shell of frozen water, methane, and ammonia. To the naked eye, it's inert. But then a cosmic ray, perhaps a proton accelerated by a distant supernova, slams into it with the energy of a baseball pitch crammed into a single atom. In that violent instant, bonds shatter, atoms rearrange, and something extraordinary emerges from the chaos. A molecule like glycine or even a nucleotide base, the raw material of life's instruction manual. We've actually watched this process unfold in labs. Scientists at the University of Hawaii recreated interstellar ice analogs, ultra-cold mixtures mimicking the frost on space dust, then bombarded them with proton beams simulating cosmic rays. Within hours, the irradiated ices spawned organic compounds far more complex than the starting ingredients. Even more astonishing, some of these molecules showed chirality, a subtle preference for left or right-handedness that's a hallmark of biological chemistry. It's as if the sheer violence of cosmic rays doesn't just create randomness, it nudges molecules toward the specific configurations life would later exploit. The real magic lies in cosmic rays' persistence. Unlike fleeting lightning strikes or localized vents, these particles pepper every corner of the galaxy, delivering a steady drizzle of energy to even the most remote molecular clouds. NASA's Stardust mission found evidence of this when it captured interstellar dust grains laced with unusual isotopes, telltale signatures of cosmic ray bombardment. And because cosmic rays penetrate deep into ice and rock, they could have forged complex molecules in places shielded from destructive starlight, like the subsurface oceans of Europa or the cracks in asteroid interiors. But here's the twist: cosmic rays don't work alone. Recent experiments show they team up with other space phenomena in unexpected ways. When ices containing formaldehyde were zapped with cosmic rays followed by ultraviolet light, mimicking the dual assault of deep space, the yield of sugars like ribose skyrocketed. It's a one-two punch. Cosmic rays provide the initial energy to break stubborn bonds, while gentler photons help reassemble the pieces into biologically useful forms. This synergy might explain why meteorites like Murchison contain such a rich variety of organics. They were cosmic ray targets for millions of years before landing on Earth. Critics point out that while cosmic rays excel at making small molecules, building chains long enough to store genetic information remains a hurdle. Yet proponents counter with a clever idea: radiation's effects might be cumulative. Each cosmic ray strike could add another link to a growing molecular chain, like a slow-motion polymerization factory. Supporting this, researchers at the University of Sherbrooke observed peptide short protein fragments forming in irradiated ice mixtures over weeks of exposure. What makes this theory so compelling is its sheer ubiquity. Every planet, every moon, every drifting speck of dust in the galaxy is bathed in cosmic rays. If they can indeed forge life's precursors under frozen, airless conditions, then the universe might be quietly manufacturing the ingredients for life everywhere. No oceans or atmospheres required. Next time you hear about a supernova halfway across the galaxy, remember, the particles it hurls into the void might one day seed chemistry in a place we've yet to discover. Now imagine a shoreline from 4 billion years ago where the tide rolls in and out like clockwork, leaving shallow pools to bake under the sun before flooding them once more. This rhythmic dance of wet and dry wasn't just geological routine. It could have been the universe's first assembly line for complex molecules. Tidal pool cycling hinges on a deceptively simple idea. Each evaporation phase concentrates dissolved compounds, nudging them closer together, while the return of water provides fresh ingredients and energy for new reactions. Over countless cycles, this push and pull might have transformed simple building blocks into chains long enough to store information, like RNA, the molecular cousin to DNA that many scientists believe was life's first genetic material. Laboratory experiments bring this theory to life. When researchers at the University of Munich recreated prehistoric tidal pools in dishes, alternating between wet phases with nucleotide soups and dry phases simulating evaporation, something remarkable happened. Within just 20 cycles, they observed molecules linking into strands up to 100 units long, far surpassing what static solutions could produce. The drying phase didn't just remove water, it acted like a molecular vise, squeezing nucleotides into alignment so bonds could form more easily. Then, the rewetting phase would rinse away reaction byproducts that might otherwise inhibit further growth, effectively resetting the system for the next round. But the real magic lies in the selectivity of these cycles. Modern experiments show that wet-dry conditions favor the survival of certain RNA-like molecules over others. Strands with useful properties like the ability to fold into shapes that resist breakdown persist through multiple cycles, while weaker ones disintegrate. It's a primitive form of molecular evolution where the tidal rhythm itself becomes the editor, preserving what works and discarding what doesn't. Critics often question whether early Earth had enough stable shorelines for this process to matter. Yet geological evidence suggests tidal zones might have been more extensive than we think. Before continents rose to their current heights, vast shallow seas could have created millions of kilometers of evaporating coastline. Even more compelling, similar reactions work in simulated volcanic terrains where acidic pools undergo natural cycling, proving the concept isn't limited to marine environments. What makes this theory so elegant is its universality. From the salt flats of Chile to the seasonal lakes of Mars, wet-dry cycles exist across the cosmos. And unlike rare events like asteroid strikes, this process is relentless, a patient, repeating drumbeat that could have slowly but surely built complexity from simplicity. The next time you see a tide pool glistening in the sun, consider this. Within its temporary borders, the universe might have run its first experiments in molecular persistence. Deep beneath the ocean's surface, where Earth's crust cracks and bleeds heat, a quieter, gentler cousin to the black smoke of vents might hold the secret to life's first power source. Forget the acidic, metal-rich plumes of traditional hydrothermal vents. Alkaline vents like the Lost City hydrothermal field near the mid-Atlantic ridge operate on an entirely different chemical logic. Here, seawater percolating through mineral-rich rock reacts with olivine and other mantle minerals, producing warm, alkaline fluids rich in hydrogen and bubbling with tiny mineral chimneys that resemble frozen cappuccino foam. These porous, labyrinthine structures aren't just geological oddities. They're natural batteries humming with proton gradients that could have jump-started life's very first energy transactions. The brilliance of alkaline vents lies in their built-in energy asymmetry. Where acidic vents blast scorching, corrosive fluids, alkaline systems create a subtle but powerful imbalance, like a microscopic version of a dam separating high water from low. The vent fluids, packed with hydrogen and lacking protons, meet the more acidic ocean water across the mineral wall's nanoscale pores. This sets up a natural voltage difference, with protons constantly trying to equalize across the barrier. Modern cells use nearly identical proton gradients to power their energy currency, leading some scientists to argue life didn't invent this trick, it inherited it from geology itself. Lab experiments lend startling support to this idea. When researchers at University College London recreated alkaline vent conditions in glass reactors, they observed iron-sulfur minerals spontaneously forming microscopic wires capable of conducting electrons, a rudimentary electrical grid. Even more compelling, these systems generated small organic molecules like acetate, a key metabolic intermediate. It's as if the vents weren't just serving up ingredients, but the very blueprint for how to use them. Yet the vent debate isn't settled. Critics note that while proton gradients are universal in biology, linking them directly to vent chemistry requires more evidence. Some propose hybrid models where vent-borne molecules later organized in tidal pools or volcanic pores. Others highlight that alkaline vents, while elegant, were likely rarer than their acidic counterparts in Earth's youth. But proponents counter with a poetic twist. Rarity might have been the point. Life needed a Goldilocks environment, not too harsh, not too passive, and these mineral cascades, with their steady energy drip and protective microchambers, could have been the universe's first charging stations. What makes this theory resonate is its elegant economy. Instead of imagining life inventing energy systems from scratch, it suggests the planet handed them over ready-made, a gift wrapped in mineral walls and proton flows. Next time you feel the buzz of your own cellular metabolism, remember, that spark might trace back to a 4-billion-year-old undersea chimney, quietly humming with the same chemistry that powers you today. Phosphorus might be one of the rarest elements in the cosmos relative to its biological importance, but without it, life as we know it would simply not exist. This unassuming element, tucked away in the periodic table, forms the backbone of ATP, the energy currency powering every cell in your body, and provides the structural scaffolding for DNA itself. Yet here's the cosmic irony: while phosphorus is essential, it's notoriously scarce in forms that biology can use. Most of it gets locked away in insoluble minerals, stubbornly refusing to dissolve in water or participate in the delicate dance of prebiotic chemistry. So how did this reluctant element become a cornerstone of life? The answer might lie in two radically different sources: meteorites smashing into our young planet, or exotic land environments where geology performed alchemical tricks to free phosphorus from its mineral prison. Let's start with the extraterrestrial angle. When scientists analyze carbonaceous chondrites, the crumbly, primitive meteorites that date back to the solar system's birth, they find something startling. These space rocks contain phosphorus in forms far more soluble than Earth's native minerals. Specifically, a compound called schrebersite, an iron-nickel phosphide that reacts eagerly with water, releasing phosphorus ions ready to join organic reactions. The Murchison meteorite, famous for its amino acids, also carries schreibersite, and lab experiments show that when this mineral mingles with warm water and simple carbon compounds, it can produce phosphorylated molecules like those found in ATP. It's as if the universe packaged phosphorus in a bio-friendly form and delivered it via celestial FedEx. But here's where the debate ignites. While meteorites provide a compelling delivery mechanism, pinning life's phosphorus supply entirely on space rocks raises tough questions. Calculations suggest the late heavy bombardment, the era of pummeling asteroids 4 billion years ago, might not have delivered enough schreibersite to stock the primordial soup adequately. That's where terrestrial theories step in. Picture a volcanic landscape dotted with acidic hot springs, their waters rich in dissolved phosphate compounds. Recent studies of Iceland's geothermal fields reveal that when acidic fluids seep through certain volcanic rocks, they can leach out phosphorus in forms usable by biochemistry. Even more intriguing, the same environments often contain clays and metal catalysts that help link phosphorus to organic molecules, creating phosphate esters, the critical bonds found in ATP and RNA. The most unexpected twist, however, comes from a vanishingly rare type of land environment, soda lakes. These alkaline bodies of water, like California's Mono Lake or Tanzania's Lake Natron, harbor conditions so unusual they force phosphorus to behave differently. Under high pH, normally insoluble phosphate minerals dissolve more readily, while carbonate ions help stabilize phosphorylated intermediates. In 2021, researchers demonstrated that soda lake conditions could synthesize acetyl phosphate, a simpler cousin of ATP, without any biological help. If similar lakes existed on early Earth, they might have been phosphorus supermarkets, stocking the shelves with life's future energy molecules. What makes this puzzle so fascinating is its duality. Meteorites offer a dramatic, one-time infusion of reactive phosphorus, while land-based processes provide a slow but steady supply. The truth might lie in a combination asteroid seeding the initial inventory, with geological systems amplifying and refining it. Either way, phosphorus scarcity wasn't a roadblock for life. It was a bottleneck that forced creativity, shaping the very pathways metabolism would later follow. Next time you feel a surge of energy after a meal, thank those ancient cosmic and geological conspirators for turning a stubborn element into life's silent powerhouse. Hydrogen cyanide might sound like the last ingredient you'd want in life's recipe, a deadly poison to most organisms today. But rewind 4 billion years, and this simple molecule could have been the universe's secret weapon for building the very foundations of life. Floating in the frigid depths of space or simmering in Earth's primordial pools, hydrogen cyanide, just one atom of hydrogen, one of carbon, and one of nitrogen, holds a remarkable property. Under the right conditions, it can spontaneously stitch itself into adenine, one of the 4 crucial nucleobases that form DNA and RNA. It's as if the cosmos embedded a molecular cheat code in one of its most common compounds, a way to bootstrap complexity from simplicity. The chemistry is as elegant as it is surprising. When hydrogen cyanide molecules collide in the presence of energy, whether from ultraviolet light, heat, or even cosmic rays, they begin linking up like beads on a string. First, they form dimers, then trimers, and eventually a web of interconnected chains. At a certain threshold, these chains start folding back on themselves, rearranging into ring-shaped structures. And here's the magic. One of those rings is adenine, the A in the genetic alphabet. Scientists have recreated this process in labs by exposing hydrogen cyanide to conditions mimicking early Earth or interstellar space. In one striking experiment at Georgia Tech, researchers mixed hydrogen cyanide with ammonia and water, then zapped the solution with ultraviolet light. Within days, adenine crystals began forming at the bottom of their flasks, a vivid demonstration of how effortlessly life's building blocks can emerge from basic chemistry. But hydrogen cyanide's talents don't stop there. The same polymerization process can yield guanine, another DNA nucleobase, as well as amino acids like glycine. Even more astonishing, when hydrogen cyanide reacts with formaldehyde, another molecule plentiful in space, it can produce sugars like ribose, the R in RNA. This means a single, abundant molecule could have supplied multiple critical ingredients for life's earliest systems, all through variations of the same fundamental reactions. The real kicker, hydrogen cyanide, isn't some rare cosmic delicacy. It's everywhere. Astronomers have detected it in the atmospheres of Titan, in the tails of comets, and in the vast molecular clouds where stars are born. The Rosetta mission even found it wafting from comet 67P, its bitter almond scent frozen in the ice. On early Earth, volcanic eruptions and asteroid impacts would have churned out hydrogen cyanide in staggering quantities, creating a steady supply for these reactions to exploit. Critics, though, highlight a paradox. While hydrogen cyanide polymerization works beautifully in controlled lab settings, could it have been efficient enough in the messy real world? The answer might lie in nature's talent for concentration. Tidal pools evaporating under the sun or freezing ice pockets in space could have amplified the process by squeezing hydrogen cyanide molecules into tight spaces, increasing their chances of colliding and reacting. Recent simulations show that under freezing conditions, hydrogen cyanide ices can form adenine at rates 1,000 times faster than in liquid solutions, a nod to how cold space environments might have been ideal factories for these transformations. What makes this theory so captivating is its duality. Hydrogen cyanide is both destroyer and creator, a molecule that modern life shuns but ancient chemistry might have relied upon. It's a reminder that the universe doesn't play by our rules. What's toxic today could have been the spark that set the whole story in motion. Formaldehyde might seem like a humble starting point, just one carbon, one oxygen, and two hydrogen atoms, but in the crucible of early Earth, this unassuming molecule could have orchestrated a sugar rush that set the stage for life's sweetest building blocks. Enter the foremost reaction, a wild cascade of chemistry that transforms simple formaldehyde into a dizzying array of sugars, including ribose, the backbone of RNA. Picture a warm, shallow pool under an ancient sun, its waters laced with formaldehyde seeping from volcanic vents or raining down from space. Add a pinch of minerals like calcium hydroxide as catalysts, and something extraordinary happens. The molecules begin linking up like microscopic Lego blocks, spinning out chains of sugars in a process so prolific it's been called chemical chaos. The brilliance of the foremost reaction lies in its spontaneity. Unlike finicky laboratory syntheses that demand precise control, this reaction thrives on randomness. Formaldehyde molecules first dimerize into glycolaldehyde, a two-carbon sugar, which then becomes the seed for longer chains. Like a molecular snowball rolling downhill, the reaction rapidly escalates, producing 3, 4, 5, and 6 carbon sugars, including ribose, in a frenzied burst of activity. Scientists have recreated this process in labs, watching as clear formaldehyde solutions turn amber with sugar complexity within hours. It's a vivid demonstration of how easily the universe could have stocked its pantry with life's essential carbohydrates. But there's a catch. The foremost reaction doesn't just produce ribose, it generates a riot of other sugars, many of which are useless or even hostile to biology. Ribose, fragile and prone to degradation, often ends up as a minor player in this molecular free-for-all. Critics argue that without a way to filter out the noise to isolate and protect ribose from its chaotic siblings, the reaction might be too messy to explain life's precise sugar preferences. Some researchers compare it to baking a cake by throwing flour, sugar, and eggs into a tornado and hoping for a perfect layer cake to land on the counter. Yet nature might have had a workaround. Recent experiments reveal that certain minerals, like borate, can stabilize ribose long enough for it to participate in further reactions. Clays with layered structures could have acted as molecular sieves, selectively trapping ribose while letting other sugars wash away. Even more intriguing, the foremost reaction isn't a one-way street. Under the right conditions, it can self-regulate with feedback loops that favor certain products over time. This hints that what looks like chaos might conceal hidden order. A subtle bias toward the sugar's life would later enshrine. The debate isn't just academic. If the foremost reaction was indeed a key player in prebiotic chemistry, its fingerprint should be everywhere, not just on Earth but across the cosmos. Astronomers have already spotted formaldehyde in molecular clouds and comets, suggesting the raw ingredients for sugar synthesis are universal. And if ribose could emerge from such chaos, even fleetingly, it forces us to reconsider how much randomness life can tolerate or even exploit in its quest to get started. Sometimes the universe's most revolutionary breakthroughs might arise not from precision but from a glorious, untamed jumble. Forget everything you know about the origins of life starting with genetic material. What if the first spark of complexity wasn't RNA or proteins but something far simpler, oily droplets that could spontaneously organize themselves? This is the radical premise of the lipid world hypothesis, which flips the traditional script by suggesting that membranes came first, acting as nature's original containers long before biology invented its molecular machinery. Picture a primordial pond not as a soup of loose chemicals, but as a seething mass of microscopic bubbles, each one a tiny fortress protecting precious cargo from the chaos outside. These weren't cells as we know them, but their ancestors' self-assembling lipid structures that might have kick-started life's journey by creating the very first compartments where chemistry could experiment in peace. Lipids, those unassuming molecules that make up cell membranes today, have a remarkable talent. Put them in water, and they spontaneously arrange themselves into sheets and spheres, their water-loving heads facing outward and their water-repelling tails tucked inside. This isn't just a neat trick, it's a fundamental property of physics, one that could have allowed primitive membranes to form without any guidance from genes or enzymes. Experiments with simple fatty acids, like those found in meteorites or simulated prebiotic conditions, show they readily assemble into vesicles, hollow spheres that grow, divide, and even fuse with one another. These microscopic bubbles aren't just passive bags, they're dynamic systems capable of concentrating molecules inside their protective walls and creating microenvironments where reactions can flourish. But here's where the theory gets truly compelling. Unlike fragile RNA strands that degrade easily, lipid membranes are robust. They can withstand temperature swings, pH changes, and even the harsh radiation of early Earth. More importantly, they solve one of prebiotic chemistry's biggest puzzles: how to keep useful molecules together long enough to interact meaningfully. Without membranes, promising compounds would diffuse into the vastness of the ocean, lost forever. But inside a lipid vesicle, they're trapped like ingredients in a tiny kitchen, forced to collide and react. Researchers at Harvard demonstrated this by creating vesicles that selectively absorbed nucleotides from their surroundings, then concentrated them up to 1,000 times higher inside, a potential game-changer for RNA formation. Critics, however, point out a glaring hurdle. How could these primitive membranes evolve without genetic material to guide them? The answer might lie in the lipids themselves. Certain fatty acids can act as rudimentary catalysts, accelerating reactions within their own walls. Others change their permeability based on temperature or pH, creating natural feedback loops. In 2021, a team at the University of Strasbourg observed vesicles made of simple lipids developing unexpected complexity. Some became better at retaining useful molecules, while others split asymmetrically, producing daughter vesicles with slightly different properties. It's a ghost of Darwinian competition at the molecular level, where the most stable or efficient structures persist while others fade away. What makes this hypothesis so tantalizing is its universality. Lipids aren't rare or exotic. They've been detected in meteorites, interstellar clouds, and simulated prebiotic syntheses. If membranes truly came first, then the path to life might not have required a miraculous stroke of chemical luck, just the patient self-organization of molecules following nature's most basic rules. Next time you look at a soap bubble shimmering in the light, consider this. The same physics that creates its iridescent beauty might have once built the universe's first living structures, one oily droplet at a time. Imagine a molecular dance so intricate that neither partner could exist without the other peptides and nucleotides twirling in perfect synchrony, each one stabilizing the other as they evolved side by side. This is the essence of peptide-nucleotide coevolution, a theory that challenges the classic, which came first debate by suggesting these two pillars of life didn't emerge separately, but grew up together in a mutually reinforcing embrace. Picture Earth's shallow pools 4 billion years ago, where short protein-like peptides and primitive RNA-like strands might have formed a partnership so beneficial, it became the foundation for everything that followed. At the heart of this idea lies a simple but profound principle. Peptides and nucleotides each solve the other's greatest weakness. RNA nucleotides, while capable of storing genetic information, are notoriously fragile, prone to unraveling in water or breaking apart under ultraviolet light. Peptides, on the other hand, lack the ability to replicate or carry instructions, but they're tough, versatile, and can fold into shapes that protect or catalyze reactions. When combined, they create something greater than the sum of their parts. Experiments at the MRC Laboratory of Molecular Biology demonstrated this synergy by mixing short peptides with RNA strands. The peptides wrapped around the RNA like molecular Velcro, shielding it from degradation, while the RNA's negative charge helped organize nearby peptides into more stable structures. It's a partnership that hints at how early chemistry might have bootstrapped its way toward complexity. But how could such a system evolve without existing biological machinery? The answer might lie in a phenomenon called phase separation. In certain salt concentrations or temperatures, mixtures of peptides and nucleotides spontaneously form dense droplets, microscopic hubs where molecules concentrate dramatically, increasing their chances of interaction. Researchers at Stanford recreated these conditions in test tubes, watching as droplets enriched with both peptides and RNA precursors selectively absorbed molecules that enhanced their stability. Over time, these droplets could have acted as primitive cells, nurturing combinations that worked while shedding those that didn't. The most compelling evidence comes from modern biology itself. Ribosomes, the molecular machines that translate RNA into proteins, are essentially hybrids, part RNA, part peptide. Their very structure suggests an ancient collaboration where RNA handled information storage while peptides provided structural support and catalytic power. Even more telling, some of life's most fundamental reactions, like protein synthesis, rely on RNA's ability to recognize amino acids, a relic of a time when these molecules might have selected each other from a chaotic chemical pool. Critics argue that while coevolution elegantly bridges the gap between chemistry and biology, it still leaves questions about how the first peptides and nucleotides found each other in a vast prebiotic soup. Yet supporters point to environments like volcanic pore networks or tidal pools, where cycles of wetting and drying could have concentrated both classes of molecules simultaneously. What makes this theory so captivating is its refusal to choose sides. It's not the RNA world or the protein world, but a universe where life's essential molecules grew up together, each lifting the other toward the threshold of the living. The next time you marvel at the precision of your own cellular machinery, remember, its roots might stretch back to a time when cooperation wasn't just helpful but the only way forward. Among life's most puzzling quirks is its stubborn preference for left-handed amino acids, a molecular bias so consistent it feels like the universe thumbed the scales. Every protein in your body, from muscle fibers to brain chemicals, is built exclusively from these left-twisting variants, while their mirror image right-handed counterparts are conspicuously absent. This isn't just a biological curiosity, it's a cosmic riddle. Why would nature favor one molecular version over its perfect reflection? The answer might lie in forces far beyond Earth's shores, from the polarized starlight filtering through interstellar clouds to the sway of ancient magnetic fields nudging chemistry toward asymmetry. One compelling clue comes from deep space. When astronomers analyze the light passing through vast molecular clouds, they notice something odd. It's polarized, twisted ever so slightly by dust grains aligned with magnetic fields. This subtle filtering could have imprinted its bias on the molecules forming within those clouds. Experiments at the National High Magnetic Field Laboratory support this idea. When scientists shone polarized ultraviolet light on a mix of amino acid precursors, the resulting molecules showed a slight but measurable preference for left-handed forms. It's as if the universe's lighting rig was set to a cosmic default, favoring one twist over another from the very beginning, but magnetic fields might have doubled down on this bias. Early Earth's geodynamo, churning with ferrous fluids, could have created localized zones where certain molecular orientations stabilized better than others. Researchers at the University of Tokyo recreated these conditions by subjecting amino acid solutions to strong magnetic fields in rotating chambers. Over time, the left-handed versions began to dominate, suggesting our planet's own magnetic personality might have amplified a faint cosmic preference into a biological mandate. The plot thickens when we consider radioactive decay. Certain isotopes like carbon-14 emit electrons that spin preferentially in one direction, a phenomenon called parity violation. When these particles interact with molecules, they can selectively break apart right-handed amino acids while leaving left-handed ones intact. French chemist André Braque demonstrated this by bombarding amino acid mixtures with beta particles, watching as the left-handed survivors accumulated. It's a reminder that even the subatomic quirks of physics might have quietly shaped life's molecular toolbox. Yet skeptics argue these effects are too weak to explain life's near-perfect homochirality. That's where autocatalysis enters the story, a process where molecules can amplify tiny initial biases into overwhelming majorities. Imagine a pond where left-handed amino acids, even slightly more common, happen to form chains faster. These chains then act as templates, reinforcing their own-handedness in a snowball effect. Japanese chemist Kenso Soe proved this works by creating a reaction where a 5% initial bias spiraled into near-total dominance within hours. What makes this mystery so captivating is its universality. The same left-handed bias appears in meteorites like Murchison, suggesting Earth didn't act alone. Whether sculpted by starlight, magnets, or quantum quirks, life's asymmetry might be written into the fabric of reality itself, a silent twist in the plot that made all the difference. Quantum mechanics isn't just the domain of subatomic particles, it might have been the unseen hand guiding the universe's first molecules toward complexity. At the coldest, smallest scales, particles behave in ways that defy classical logic. Electrons exist in multiple places at once. Atoms tunnel through barriers like ghosts, and entangled particles instantaneously influence each other across vast distances. These aren't just oddities, they could be the secret ingredients that made life's precursors possible. Take photosynthesis, a process so efficient it borders on the impossible. Plants and bacteria achieve near-perfect energy transfer by leveraging quantum coherence, where excitations exist in multiple molecular paths simultaneously, essentially testing all routes at once to find the most efficient one. If modern biology exploits these effects, could quantum weirdness have also given prebiotic chemistry a crucial nudge? Laboratory experiments hint at tantalizing possibilities. In 2020, a team at the University of Chicago observed quantum coherence in synthetic molecules designed to mimic early Earth conditions. When exposed to ultraviolet light plentiful on our young planet, these structures exhibited fleeting moments where electrons delocalized across multiple atoms, temporarily stabilizing bonds that would otherwise be too fragile to persist. It's as if quantum mechanics provided a microscopic safety net, allowing precarious molecular arrangements to survive just long enough to catalyze the next critical reaction. Even more startling, simulations of interstellar ice analogs show that quantum tunneling, where hydrogen atoms teleport through energy barriers, can accelerate the formation of complex organics by factors of 1,000,000 in frigid space environments. The real mind-bender, quantum entanglement, might have played a role. While typically associated with particles like photons, some researchers speculate that entangled states could have emerged between molecules on ancient mineral surfaces, synchronizing their reactions across distances. Imagine two amino acids forming on opposite sides of a clay particle, their fates linked by quantum correlation so that when one twists left, the other follows suit, a potential explanation for life's universal handedness. This isn't pure speculation. Studies of magnetite crystals under prebiotic conditions show they can host entangled electron pairs, creating local zones where chemistry operates under quantum rules rather than classical randomness. Critics rightly caution that quantum effects are fragile, easily destroyed by heat or noise. But early Earth offered pockets where these conditions might have aligned. Ice caves shielding molecules from thermal disruption, or mineral matrices acting as quantum simulators. The deeper we look, the more it seems life didn't just adapt to quantum mechanics. It may have been built by it, one coherent superposition at a time. Beneath the ocean's crushing depths, where scalding plumes of mineral-rich water blast from towering black smoker chimneys, nature might have perfected its first molecular tools. These otherworldly vents, belching superheated fluids at temperatures exceeding 700 degrees Fahrenheit, aren't just geological spectacles. They're dynamic workshops where metal ions act as master craftsmen, forging bonds between simple molecules with ruthless efficiency. Picture a labyrinth of porous sulfide minerals, each pore drenched in iron, nickel, and copper ions leached from Earth's mantle. To modern eyes, it's a hellscape. But to prebiotic chemistry, it could have been the ultimate proving ground, a place where metal catalysis turned chaotic soups of carbon and nitrogen into the structured building blocks of life. The magic lies in the metal's electron dance. Iron and nickel ions, abundant in black smoker fluids, excel at shuffling electrons between molecules like microscopic croupiers dealing cards. This isn't abstract theory, we've seen it in action. Modern extremophile microbes thriving near these vents today rely on metal enzymes with structures so ancient they're practically molecular fossils. Take hydrogenase, an enzyme that splits hydrogen gas with breathtaking precision. At its core, an iron-nickel cluster eerily similar to the mineral greigite found in vent deposits. Or consider nitrogenase, which cracks atmospheric nitrogen's brutal triple bond using a molybdenum iron cofactor, a structure that could have first assembled spontaneously in vent pores. These aren't coincidences, they're clues that life didn't invent metal catalysis, it inherited it from geology. Lab experiments amplify these connections. When researchers at the University of Tokyo simulated black smoker conditions by mixing iron sulfide with carbon monoxide and hydrogen sulfide, common vent gases, they watched as the mixture began producing acetate, a key metabolic intermediate. Even more striking, the reaction pathways mirrored those used by modern microbes, suggesting chemistry here didn't just stumble toward life, it followed a pre-paved road. Another study showed nickel ions, abundant in vent fluids, could stitch together amino acids into short peptides at temperatures matching vent environments. It's as if the vents were running their own molecular boot camp, training simple compounds to behave like biology long before cells existed. But the real genius of black smokers lies in their gradients. Where scorching vent fluid meets frigid seawater, a kaleidoscope of microenvironments emerges, each with its own pH, temperature, and metal concentration. This isn't chaos, it's a spectrum of chemical possibilities. A molecule formed in the blistering core might drift outward, encountering slightly cooler zones where it stabilizes, then zones where it links with others. Recent work at the Woods Hole Oceanographic Institution demonstrated how these gradients can selectively concentrate reactive intermediates, effectively creating an assembly line where each station adds another piece to the growing puzzle of complexity. Critics argue that while metal catalysis is potent, black smoker's harsh acidity and heat might destroy more than they create. Yet extremophiles like Pyrolobus fumariae, thriving at 235 degrees Fahrenheit near vents, prove stability is possible. And new discoveries of lost city-type alkaline vents with gentler conditions but similar metal chemistry suggest the process wasn't confined to hellish environments. What makes this theory so compelling is its dual legacy. The same metals that once forged life's first molecules still pulse at the heart of your cells today, a 4-billion-year testament to the enduring power of Earth's deepest alchemy. The young Earth's atmosphere wasn't the oxygen-rich blanket we know today. It was a thick, hazy shroud brimming with hydrogen, methane, and carbon dioxide, a mix so alien it might as well be from another planet. Yet this very strangeness could have been the catalyst for life's first molecular experiments. Enter the hydrogen-rich atmosphere theory, where simple gases like CO2, often dismissed as a dead-end molecule, transformed into life's precursors through the quiet, relentless pull of hydrogen's chemistry. Imagine a world where the air itself acted as a giant reducer, stripping oxygen atoms from carbon dioxide and leaving behind reactive fragments eager to form something new. Laboratory doors have swung open on this idea with startling results. When scientists at the University of Strasbourg recreated early Earth's atmosphere in sealed flasks, filling them with hydrogen, carbon dioxide, and traces of iron minerals as catalysts, something remarkable happened. Within days, the mixture began producing formate, acetate, and even pyruvate, molecules that sit at the heart of modern metabolism. The process, called hydrogen-dependent CO2 fixation, mirrors how some of Earth's oldest microbes still generate energy today. It's as if the experiment had tapped into a primordial recipe, one where the very air we now exhale as waste became the starting material for life's first sparks. What makes this reaction so elegant is its simplicity. Unlike lightning strikes or asteroid impacts, which rely on violent, localized energy, hydrogen reduction works silently and universally. Everywhere the atmosphere touched, whether the surface of a tidal pool or the pores of a volcanic rock, it could have been driving the same chemistry. Recent experiments added an unexpected twist. When researchers included tiny amounts of nickel or cobalt, the yields of organic molecules skyrocketed. These metals, abundant in Earth's early crust, might have acted like molecular matchmakers, lowering the energy barrier for reactions that would otherwise stall. But the real kicker, this process isn't confined to Earth. The same hydrogen-rich atmospheres might exist right now on exoplanets orbiting red dwarfs, where intense stellar radiation could maintain similar reducing conditions. Telescopes like JWST are already hunting for signs of these chemical imbalances, a hint that the universe might be running this experiment on countless worlds. Critics point out that maintaining a hydrogen-rich atmosphere requires specific planetary conditions, like limited volcanic outgassing or a lack of ultraviolet-driven hydrogen escape. Yet supporters counter with evidence from ancient zircon crystals, which preserve chemical fingerprints of Earth's early air. Their analysis suggests hydrogen levels could have remained high enough for millions of years, especially if methane, a potent hydrogen reservoir, was abundant. The implications are profound. If hydrogen reduction truly built life's early toolkit, then planets we'd once written off as too reducing might in fact be the best incubators for complexity. It's a humbling reminder that life's origins might not demand the Goldilocks conditions we assume, just the quiet, persistent pull of chemistry playing out across an entire planetary stage. Deep in the frigid darkness between stars, dust grains cloaked in ice might have served as the universe's most unexpected molecular workshops. These aren't just frozen specks, they're dynamic microenvironments where chemistry unfolds in ways impossible in open space. Picture a grain no wider than a human hair, its surface a patchwork of frozen water, carbon monoxide, and ammonia. Bombarded by cosmic rays and ultraviolet light, these ices don't stay inert. They become reactive arenas where molecules fracture, migrate, and recombine in the shelter of their frozen matrix. The Rosetta mission's study of comet 67P revealed just how potent this process can be. The spacecraft detected glycine, the simplest amino acid embedded in the comet's icy crust, a smoking gun for chemistry occurring far from any planet or star. What makes ice grains so effective is their layered structure. As molecules freeze onto a grain's surface, they arrange into crystalline or amorphous lattices that can trap and concentrate reactants. Ultraviolet radiation penetrating these ices doesn't just break bonds. It creates radicals, highly reactive fragments that skitter through the ice until they find partners. Laboratory simulations at NASA, a jet propulsion laboratory, show that under space-like conditions, these radicals can form complex organics like ethanol and even ribose, the sugar backbone of RNA. The ice acts like a protective mold, preventing newly formed molecules from flying apart while allowing just enough mobility for reactions to proceed. But the real breakthrough came when scientists noticed something peculiar about comet 67P's chemistry. The glycine they found wasn't isolated. It appeared alongside methylamine and ethylamine, compounds known to facilitate peptide bond formation. This suggests ice grains weren't just making building blocks. They might have been assembling them into more sophisticated structures. Modern experiments confirm this. When researchers irradiate ice analogs containing these molecules, they observe short peptide chains forming spontaneously. It's as if the universe baked life's ingredients into its coldest, most unassuming materials. The implications stretch beyond comets. Europa's icy crust and Enceladus's plumes likely host similar processes today, with grains cycling between surface radiation and subsurface oceans. Even interstellar clouds, where temperatures hover near absolute zero, could be silently manufacturing complexity in these frozen nanolabs. The next time you see frost glittering in sunlight, consider this. The same physics that creates winter's beauty might have once crafted the first whispers of life, one icy grain at a time. Silicate surfaces might seem like unlikely players in life's origin story, just grains of sand or powdered rock to the naked eye. But zoom in closer, and these unassuming minerals reveal a hidden talent. They can act as molecular scaffolds, organizing chaotic soups of organic compounds into orderly patterns that could have paved the way for life's first complex structures. Picture the dusty plains of early Earth or Mars, where windswept particles of silica, the same stuff that makes up quartz and flint, formed vast, undulating dunes. On these microscopic landscapes, something extraordinary was happening. As molecules like amino acids or nucleotides bumped into the silicate surfaces, they didn't just bounce away. They stuck, and not randomly. Certain surfaces attracted specific molecules, aligning them in precise orientations that made chemical reactions far more likely. This isn't just speculation. Experiments with Martian soil simulants meticulously crafted mixtures mimicking the composition of the red planet's regolith have proven the concept in striking detail. When scientists at NASA, a Goddard Space Flight Center, exposed these faux Martian silicates to solutions containing RNA precursors, the minerals didn't just passively host the molecules. They actively curated them, selectively binding nucleotides in ways that encouraged them to link into chains. Silica's secret lies in its charged surface patches and porous structure, which create pockets where molecules nestle like puzzle pieces. Some silicate varieties even exhibit chirality, subtly favoring left or right-handed molecular forms, a potential explanation for life's universal preference for one symmetry over another. But the real magic happens when environmental rhythms enter the equation. Tidal pools or seasonal rivers on early Mars or Earth would have subjected these silicate-bound molecules to cycles of wetting and drying. Each evaporation phase would have pushed molecules closer together on the mineral surfaces, increasing the odds they'd react. Then, when water returned, it could have flushed away unwanted byproducts, resetting the stage for the next round. Lab simulations of this process have yielded eye-opening results. Silicate surfaces under wet-dry cycling produce RNA-like strands up to 10 times longer than those formed in solution alone. Critics argue that while silicates excel at organization, they might struggle with diversity. After all, life relies on many molecular types interacting in concert. Yet recent work with layered clays, which often interleave with silicates, suggests a solution. These minerals can host different molecules in separate layers, allowing parallel chemical pathways to unfold without interference. Imagine silica as a bustling molecular marketplace where reactants meet on neutral ground, trade electrons, and depart as something new. What makes this theory so compelling is its universality. Silicates aren't rare, they're the dominant minerals in Earth's crust and Mars' soil. If they could indeed shepherd randomness toward order, then the universe might not need exotic conditions to cook up life's ingredients, just ordinary dirt, patience, and the right rhythmic nudges. Next time you hold a handful of sand, consider this. Those grains might hold echoes of the universe's oldest molecular choreography, a dance of attraction and alignment that set the stage for everything that followed. Volcanic fields might seem like the last place you'd expect life's ingredients to simmer into existence until you consider how a pizza oven works. The Prebiotic pizza hypothesis takes this whimsical analogy seriously, proposing that certain volcanic landscapes could have acted like nature's brick ovens, baking simple gases and minerals into molecular complexity. Picture a geothermally active plain, fumaroles puffing sulfurous steam while porous volcanic rocks, riddled with microscopic nooks, trap and concentrate reacting molecules like toppings on a crust. The heat isn't scorching enough to incinerate everything, but just right to drive reactions at the Goldilocks pace needed for delicate organics to form. Support comes from modern volcanic systems like Italy's Campi Flegrei, where scientists have detected formaldehyde and hydrogen cyanide wafting from steaming vents, the same molecules that, in labs, spontaneously link into sugars and amino acids. What makes these environments special isn't just the chemistry, but the texture. Volcanic rocks like pumice and scoria are nature's Swiss cheese, their bubbles creating sheltered microreactors where gases like carbon monoxide and nitrogen can mingle with metal-rich minerals. Dutch researchers recreated these conditions by heating simulated volcanic rocks infused with iron and nickel salts, watching as the metals catalyzed the formation of acetate and pyruvate, key metabolic intermediates at temperatures matching shallow magma chambers. The real kicker, these systems self-regulate. As heat fluctuates with geothermal activity, some pores become temporary cold spots where fragile molecules stabilize, while others act as crucibles for new reactions. A study at Iceland's Krafla volcano found that mineral coatings inside fumaroles selectively absorb organic compounds, effectively creating molecular buffets where reactants are pre-sorted for efficiency. It's a far cry from the randomness of a primordial soup, more like a chef's mise en place, with ingredients prepped and waiting for the right moment to combine. Quirky as it sounds, the pizza analogy holds up in unexpected ways. Just as a wood-fired oven's uneven heat creates charred bubbles alongside gooey cheese, volcanic zones offer gradients where different reactions flourish in adjacent pores. Some might produce sugars, others amino acids, and convective currents could shuttle products between hotspots like a cosmic conveyor belt. The theory's charm lies in its defiance of stereotypes. Life's beginnings might not have required serene tidal pools or deep sea vents, but the equivalent of a rowdy, bubbling kitchen where chemistry got lucky. Critics argue that volcanic fields lack the long-term stability needed to nurture complexity. But supporters point to Yellowstone's hydrothermal systems, where organic synthesis has likely run continuously for millions of years. Others note that while volcanic chemistry excels at small molecules, bridging the gap to polymers remains a hurdle. Yet recent experiments with volcanic ash as a catalyst show it can promote peptide bond formation, suggesting these fiery landscapes might have been multitasking workshops. Ultimately, the prebiotic pizza hypothesis isn't just about volcanoes, it's about re-evaluating where complexity can thrive. If a handful of rock, heat, and gas can mimic a gourmet kitchen, then life's recipe might be simpler than we dared to imagine. Sometimes, the universe's most profound breakthroughs come not from pristine labs, but from the equivalent of a messy, aromatic pizzeria where ingredients collide in deliciously unexpected ways. For decades, the RNA world hypothesis has stood as the leading explanation for how life's molecular machinery first emerged, a compelling narrative where RNA pulled double duty as both genetic material and catalyst, bridging the gap between chemistry and biology. The elegance is undeniable. Unlike DNA, which needs proteins to replicate, RNA can store information and fold into shapes that accelerate chemical reactions, including its own copying. Experiments have repeatedly shown how RNA strands can self-replicate under the right conditions, with some even evolving new functions over generations. It's a story so tidy, it's easy to see why it's dominated origins research for years. Yet scratch beneath the surface and the RNA world reveals cracks in its foundation. The molecule's Achilles heel, its fragility, in water. The very medium where life supposedly began, RNA strands degrade alarmingly fast, their phosphate backbones snapping like twigs in a storm without the protective embrace of modern cellular machinery. Even more damning, while RNA can catalyze reactions, its repertoire is limited compared to proteins. The ribozymes we've discovered in labs are like blunt tools next to the precision scalpels of protein enzymes. How could something so finicky have bootstrapped an entire biosphere? Critics highlight another glaring hole: the sheer improbability of RNA forming spontaneously in prebiotic conditions. While scientists have synthesized RNA's building blocks, nucleotides, in labs, the process requires carefully orchestrated steps like isolating reactants or adding artificial catalysts. In the wild, free-floating nucleotides would face a gauntlet of competing reactions, with side products and destructive UV radiation likely derailing any progress toward complexity. Even if short RNA strands did form, how did they escape the fate of dissolving into chemical noise without compartments or repair mechanisms? But here's where the story takes a turn. Recent research has breathed new life into the RNA world by confronting its weaknesses head-on. Take the instability problem. Studies at the Scripps Research Institute discovered that certain minerals, like borate, can stabilize RNA against hydrolysis, effectively acting as molecular bodyguards. Others have shown how freezing temperatures like those in icy cometary grains dramatically slow RNA's degradation, buying time for replication to outpace destruction. Even the synthesis hurdle is being chipped away. In 2022, a team at Ludwig Maximilian University demonstrated how volcanic glass could have concentrated nucleotides, while wet-dry cycles linked them into chains without human intervention. Perhaps the most intriguing twist is the idea that RNA didn't work alone. Hybrid theories now suggest RNA might have partnered with peptides or lipids early on, each compensating for the other's flaws. RNA's nucleotides could have provided the informational blueprint, while peptides offered structural stability, a molecular division of labor that eventually led to the modern triad of DNA, RNA, and proteins. Fossilized remnants of this partnership might still exist in today's ribosome, where RNA forms the catalytic core but relies on proteins for scaffolding. What makes this debate so vital isn't just academic nitpicking, it's about redefining the possible pathways to complexity. If RNA truly was life's starting point, its struggles highlight the extraordinary persistence of chemistry fighting against entropy. And if it wasn't, then somewhere out there lies an even more ingenious solution waiting to rewrite our textbooks. Either way, the RNA world's legacy endures not as a finished answer, but as a roadmap guiding us toward deeper questions about how simplicity becomes sentience. From primordial soups to cosmic rays, interstellar ice grains to volcanic ovens, we've journeyed through 30 astonishing theories about how the universe's first complex molecules might have emerged. But here's the beautiful twist: these ideas aren't mutually exclusive. Just as a chef combines ingredients to create something greater than the sum of its parts, nature could have blended multiple pathways, each contributing a crucial piece to life's molecular puzzle. Maybe tidal pools concentrated meteorite-borne compounds while hydrothermal vents provided energy, or perhaps cosmic rays forged precursors in space that were later assembled on Earth by mineral surfaces. The truth likely lies in a symphony of processes, a convergence of improbable events that together tip the scales toward complexity. What makes this mystery so exhilarating is that we're still gathering the pieces. Every year, new discoveries like phosphine in Venus clouds or organic-laden asteroids reshape the debate. The universe seems to be whispering hints from every corner, from the depths of our oceans to the farthest reaches of our solar system. And that's where you come in. Which theory resonates with you? Is it the elegance of the RNA world, the raw power of asteroid impacts, or the quiet ingenuity of lipid membranes? Drop your favorite in the comments. We're all detectives in this grand cosmic investigation. If these 30 theories have taught us anything, it's that the universe is far more creative than we ever imagined. From the coldest voids to the most violent eruptions, nature finds a way to weave simplicity into complexity, chaos into order, and this is just the beginning. With missions like Europa Clipper and the James Webb Space Telescope peering deeper into the chemical fingerprints of distant worlds, we're on the brink of rewriting the story of our origins. So hit subscribe, because the next chapter in this epic is already being written, and you won't want to miss it. Until then, keep looking up, and remember, every atom in your body was once forged in the stars, part of a chain of cosmic chemistry that stretches back to the very first whispers of molecular